This now is session 2 or no-regalia 2. The lecture is circular motion. Kinematics of uniform circular motion, motion in a circle of constant radius, the constant everywhere, at constant speed. The speed changes directions because tangential, but constant. The speed velocity which changes the direction. Speed is constant. Instantaneous velocity is always tangent to circle. Tangent. Instantaneous means at any time. This acceleration is called the centripetal or radial acceleration, and it points toward the center. The point of which making the circle is this one everywhere. But acceleration is toward the center, centripetal acceleration, radial. For an object to be in uniform circular motion, there must be a net force acting on it. We already know the acceleration, so can immediately write the force. When you wheel around a circle, a bucket, or you tie a ball in a rope and you're making a circle like this, you feel like you're pulling between you and the ball. This force here. So you can write a force. Force, summation of force, all forces, it means summation of forces. If there are several forces, is equal to MAR, is equal to mv square over r. This one, v square over r, is radial acceleration or force toward the circle, toward the center of the circle. We can see that the force must be inward by thinking about a ball on a string. Think about a ball on a string, and then you will find, you will see force on ball exerted by string, this one, like a tension, as before we saw in other topics. Force on hand exerted by string. This one. Net forces that can cause a centripetal acceleration. Friction of tires on road, this one, in a banking roads, in corners, some corners, you'll see like some sort of a road bank tilted. So there will be a friction force pulling the tires, pulling a car inside the road, not to avoid it skidding or overturning there. Tension force also of chord, this also centripetal force. Gravity keeping object in orbit, like Earth or electrons around nucleus. Net forces that can cause a centripetal acceleration also, normal force also. There is no centrifugal force pointing outward. There is no centrifugal force pointing outward. It means it will act inward. What happens is that the natural tendency of the object to move in a straight line must be overcome. If the centripetal force vanishes, this is your rope. If you cut, it means it vanishes. You see this one losing the direction. Direction is trying to say, making sake like that. That's why here it doesn't happen. Doesn't happen like this. This happens this way. This moving this way. If the centripetal force vanishes, the object flies off tangent to the circle, like this one, or like that. Frequency, there's parameters there, we can find them in circular motion. Frequencies, period. Frequency, number of revolutions per second. Number of revolutions per second. This is frequency. Period, time, T. Is time it takes for one revolution. One revolution from this point to that point. Period. Period, T is equal to 1 over F frequency. Frequency units are 1 over second. Period units are seconds. Formulas for circular motion, where r is the radius of circle, t is period, v is velocity, m is mass. Average speed is equal to 2 pi r over t period. That is the average speed. You know this 2 pi r is, it means it's circumference of the circle over time. It's the distance over time, that one. Acceleration is equal to v square over r. We know that. Substitute 2 pi r over t for v. Acceleration, we want to use period in our formula here. We want to use period. We substitute, we get 4 pi r square, 4 pi square r over t square. Velocity not required. If you are given there with the period, you can use this formula for acceleration, centripetal acceleration. Net force is equal to MAR. Substitute mv square over r for A. Substitute there. This is acceleration. You substitute there, you get this one. This is net force. And when you are given with the period, you can substitute there this formula for AR, acceleration toward the center. This is centripetal acceleration. Force, net forces, you get that formula. Examples in circular motion. Now, we are in examples. You can see and to use these formulas. Whirling around. This is a ball. This is tension, a rope. The center is there, and moving around the circle. This one circle, and the Ft tension force toward the center, and the mg weight of this body. Acceleration of an example. Acceleration of a revolving ball. This one. A 150 kilogram ball at the end of the string is revolving uniformly in a horizontal circle of radius 0.6 meter as in figure above. The ball makes 22 revolutions in a second. 2 revolutions in a second. It means this one will be your period. What is its centripetal acceleration now? Horizontal circle. This is horizontal circle. It's horizontal. Solution. If the ball makes 2 complete revolutions per second, then the ball travels in a complete circle in a time interval equal to 0.2 seconds, which is its period, t. The distance traveled in this time, is the circumference of the circle, 2 by r, where r is the radius of the circle. Therefore, the ball has speed. We can see speed is equal to circumference over period. The centripetal acceleration is v square of r. Another example, force on, estimate the force a person must exert on a string, which means a tension, attached to a 0.15 kilogram ball to make the ball revolving in a horizontal circle of radius 0.6. The ball makes 2 revolutions per second. It means t is equal to 0.5 seconds, as in the example, the previous example. Summation of forces is equal to ma square, ma r. This is the centripetal acceleration, where r, we know this formula and we know period is this one, we have period, and force Ft, tension there, Ft is equal to ma, a is v square over r. You have here v square, this one v is. Calculate this now, another case, second case. First case before, we saw there, previous case is force on revolving ball horizontal. Now force on revolving ball vertical. Vertical is a vertical circle. The previous is horizontal. So you have to be very careful which situation you are in. Now we are in vertical circle. Vertical circle also, it has got its cases, assumptions in vertical circles. At bottom of this circle, the ball is here. Considerations now. At bottom, mg is downward. Mg is downward always. Downward. Ft2 tension, upward, is upward. Because center is there of the circle. Is upward. Mg down. So summation of forces previous there, summation of forces equal to MA. This one, summation of forces is equal to MA. We use this formula because we have several forces there. Summation of forces, you have this case, mg minus mmg, and this tension force toward the center, because center acceleration is toward the center, direction is this one positive, we consider. So Ft2 is positive, minus this one is negative, minus mg is equal to ma. So this ma, you substitute centripetal acceleration there, this one. From here you can calculate it easy. .515 kilogram ball at end of 0.1 meter chord, 1.0 at end of 1.1 meter chord sun vertical. Calculate speed at top of arc so ball doesn't fall. At top forces are mg. This ball can be ball, sometimes can be a bucket of water. So in this case here, this case 2, case 1 here, up. Ft2 is down because this is a string. So Ft2 down and mg down also. And acceleration also down. So all three forces are in the same direction. That's why you find plus here. Remember this case, like this one and this case also. So you substitute values, then you get V. The game of tetherball is played with a ball tied to a pole with a string, like this one, this up. This case, tetherball. It's like a cone, right? And this is a string, and you can do like this, sound like this, making a kind of circle like this here. But here, tied there, this is a pole. And this is a rope, this is a ball, making a circle. See? The game of tetherball is played with a ball tied to a pole with a string. After the ball is struck, it revolves around the pole as shown in there. In what direction is the acceleration of the ball, and what force causes the acceleration? Force is toward the center because the circle is there, this force. Here in our free body diagram, you can see here there is a mg weight force and the tension in the rope, Ft. This Ft is inclined in an angle. So you have to know this angle. You can resolve this in y, Fty, Ftx. This Ftx toward the center. It means this equals to centripetal acceleration, ma. And this one balances, weight force balances with the component of tension force upward. Acceleration is toward the pole like this here, not top. So net force is toward pole. Net force here we sum toward pole. Remember this case, acceleration is toward pole, it means toward center. Pole is at the center, toward pole here. It's not there, it's here, toward pole. Because center is this one, and centripetal acceleration is acceleration you can get in a circle. As a body or object revolving around a circle or in a vertical circle. So it's toward acceleration toward there. as we say, FGY balances with this one, which means this equal to this, or this minus this equal to 0, like this. FGX is centripetal acceleration towards the center. And it means this one equals to MA, equal to centripetal acceleration. Centrifugal is objects or devices used in laboratories, in medical labs, or in some laboratories. These ones are like this one and this one. These are test tubes. You keep sample of blood. When you keep sample of blood and you have a machine motor here, this circle, it means it shows a motor. It's revolving very, very quick with very high speed. And you put test tubes in this. There are some holes. They fix these test tubes with samples, blood or any fluid, liquids. Then you switch on a machine. It starts to revolve around with very high speed. And these test tubes, they start moving very hard. So they make like precipitations down there. And water is up here. So you can make some experiments from this solution yourself. So the first one, the center here, is called the centripetal force, or centrifugal force also. The rotor of one centrifugal force, centrifuge, rotates at 50,000 revolutions per minute. The top of a 4.0 centimeter long test tube, this one, is 6 centimeters from the rotational axis from center. It means the radius is 6 centimeters. And is perpendicular to it. The bottom of the tube is 10 centimeters from the axis of rotation. Okay, this 10 centimeters is from there, from point B, from point A to this axis here. Calculate the centripetal acceleration in G. G is at the top and the bottom of the tube. At the top, from here to there, and from here to there. 2 cases. Centripetal acceleration, we know that is v square over r, and gravity 9.8 meter per second square to find G's. Particle revolves in circle of circumference is equal to 2 pi r particles, because the blood is mixed with the particles, maybe mixed with particles. So you first find circumference of the circle using the first case, because 2 cases. Bottom, this one, this is top from here to there, and from bottom to there. Also, you will find it. We have particle revolving in a circle circumference, this one, and period we are given here. You change these ones. You change these revolutions per minute. So you change them per second. per second. These ones, this one here, this one per revolution, velocity. This one you substitute, you get acceleration. This is this one. Application of circular motion also in banked rods. We have seen there before in a centrifuge machine also, and we have seen it in these tether balls. This is another case in a vertical revolving ball, and another case in a horizontal. All these four cases you will find problems in all these cases. So you have to understand and to know all of them. In highway curves, banked and unbanked roads. This is our road. You can see the car here making a turn or corner, in a corner here. So this point here is down compared to this point here. So this car, when it's moving, it's like it's pulled toward this side, the center. I think all of us, we have experienced this pull or this situation in cars. First one car, this one first one passenger is this one. Tendency for passenger to go straight. When a car goes around a curve, there must be a net force towards the center of the circle of which the curve is an arc. This one is an arc. If the road is flat, that force is supplied by friction. Friction also can make this substitute also to avoid a car from overturning or skidding moving away from the road. Like these roads for Formula 1 race. The roads they have to make to consider this technology actually, banking. If the friction force is insufficient, the car will tend to move more near in a straight line as the skid marks show. Example for skidding on a curve: a 1,000-kilogram car rounds the curve on a flat road of radius 50 meters at a speed of 50 kilometers per hour or 14 meters per second. Will the car follow the curve or will it skid? Skid is like overturning. Assume A, the pavement is dry and the coefficient of static friction is mu s is equal to 0.6. But B, the pavement is icy. Ice is like it's a glass, and the mu s static is equal to 0.25. Forces are mg, Fn, and the horizontal Fn is normal force. Fn is a normal force. It's a normal force. Fn is a normal force. Is equal to mg. Net horizontal force to keep the car moving in a circle. Summation of forces Fr is equal to MAR. This one here is force toward the center, centripetal acceleration. You substitute, you can get the force, this force, whereas the equivalent is the coefficient of static friction that will the car follow the curve or will it skid? Okay. Skidding on a curve, dry pavement, maximum static friction of tiles 0.6. Friction force, their friction force is equal to mu s Fn. For the car not to skid, this centripetal acceleration, centripetal force should be greater than friction force. For example, this is friction force. Friction force. This should be equal. To avoid this car going away there, this force should be less than that one. Should be less than centripetal. Centripetal should be greater. Ice road, maximum static friction of tiles for ice roads. Static coefficient is equal to 0.25. You substitute in the formula, you get, and then you compare like before. Another example of skidding of banking road. You can see a picture is like this. This is our road. It's like this. In a corner. Like this. And this is our car. Weight force is always down, straight like this. And we have normal force, Fn, this one. Center is toward there. So be careful with those axes we choose. In other cases, like in a case of this case of inclined plane. In inclined planes, axes will be different from this case now. Because we are concentrating, or we are interested very much with this force here toward the center. Center is there. It's there, center. So this force is toward the center. So it means this one is a component of this force, normal force. Component of normal force toward center equal to to centripetal acceleration, or centripetal acceleration is a centripetal force is this force, the component of normal force. And the normal force here, as we are used before with the normal forces, if a body is in a flat surface, like the example before, flat surface, with no other forces, and G, weight force, normal forces from the surface of the surface. Here mg equal to normal force. But if it's inclined, it will change. Mg will be there. Normal surface in this one. See? Perpendicular to surface, always. So normal is there. So you have to consider those cases. So when you resolve this normal force, you get toward the center. You call it your x-axis. This is y-axis. The axis, these ones. Here, you are told that I've chosen axis in this style, not the other way like we did before. Okay. Our question, banking angle. A, for a car traveling with a speed V around a circle of radius R, determine a formula for the angle at which the road should be backed so that no friction is required. B, what is this angle for an expressway off-road, off-ramp curve of radius 50 meters at a design speed of 50 kilometers per hour? Car moving along horizontal circle. So, acceleration, centripetal acceleration is horizontal. Fn sine theta is equal to this component, equal to this acceleration toward the center, or say, centripetal acceleration, or centripetal force there, this one. We find cos theta minus mg, this component here. When you resolve normal force, you see this one balances with this one, this component here. No vertical motion, no vertical motion. That's why 0. You put 0. Fn is equal to mg cos theta. Now you can see you have two equations. This one in y-axis. In x-axis you have this equation, and in y-axis this one. You make Fn subject, you get this one, because you don't want Fn. Why Fn? Because Fn, we don't know it. We don't know it. It's not given. Usually you will see given mg. So that's why you want to make subject so that it can vanish. Fn must be greater than mg. Substitute for Fn in first equation. This one, this equation here. When you substitute there, you come to this tan theta via square over rg. You substitute, then you get theta, angle of banking. Newton's law of universal gravitation. If the force of gravity is being exerted on objects on Earth, what is the origin of that force? Newton's realization was that the force must come from the earth. You see a man standing on different corners of earth. This is gravitational force, Fg. Newton's realization that the force must come from the center, from the earth. He further realized that this force must be what keeps the moon in its orbit also. Because the earth, it acts like a center, and the moon experiences force from earth. The gravitational force on you is 1/2 of a third law pair. The earth exerts a downward force on you, and you exert an upward force on the earth. Like this one. This is me toward the earth, and earth toward me, towards me. When there is such a disparity in masses, the reaction force is undetectable, but for bodies more equal in mass, it can be sufficient. This is the moon, force toward gravitational force exerted on moon by Earth. This one is being pulled toward the Earth. Gravitational force exerted on Earth by the moon, this one. Therefore, the gravitational force must be proportional to both masses. By observing planetary orbits, Newton also concluded that the gravitational force must increase as the inverse of the square of the distance between the masses. This is gravitational law. Now, this one, this statement is gravitational law, universal. This one. Inverse of the square of the distance between masses, this one. In its final form, the law of universal gravitation reads, force is equal to G times mass 1 mass 2 divided by radius square, where G is constant, given there. The magnitude of the gravitational constant G can be measured in the laboratory. This is the Cavendish experiment. That is to show how they measure this constant G. Gravity near the Earth's surface is geophysical applications now, like these satellites. Several different satellites, there are communication satellites also. Now we can relate the gravitational constant to the local acceleration of gravity. We know that on the surface of the Earth, mg is equal to force of gravity is equal to gravitational force, g m of the body times m mass of the Earth over radius of Earth square. Solving for g gives G is equal to capital G me over re square. Now, knowing G and the radius of the Earth, the mass of the Earth can be calculated. If now you know G, you can calculate mass of the Earth, this one. If you rearrange G, we know it, we can get the mass of the Earth is this one. Very huge value. Gravity near the Earth's surface. Acceleration due table 5.1. Acceleration due to gravity at various locations on Earth. New York is that much. It's different. 9.8 and it's close. That's why we call 9.8. We use constant 9.8. Different values. The acceleration due to gravity varies over the Earth's surface due to altitude. You can see altitude 0, 0, 0 is very close. This one. This is a bit far. Elevation. Denver elevation is high. Pikes Peak, very high elevation. And the value is this one. The acceleration due to gravity varies over the Earth's surface due to altitude, local geology, and the shape of the Earth, which is not quite spherical. It's oval shape. Satellites and the weightlessness. Satellites are routinely put into orbit around the Earth. The tangential speed must be high enough so that the satellite does not return to Earth, but not so high that it escapes the Earth's gravity altogether. This is satellite here, launching of satellite, Kennedy Space Center. So satellites, they are launched and it moves. It has to make a circle like this, revolving around the Earth, and it's falling, free fall. These are shapes of trajectories, different trajectories. So they have got meanings in all these trajectories. This one here is elliptical shape. This one is a circular shape, which is needed a speed to achieve this shape circle. The satellite should revolve around with a speed of 27,000 kilometers per hour. To achieve elliptical shape, this one, speed must be 30,000 kilometers per hour. Escaping velocity is 40,000 kilometers per hour. This shape, the satellite will escape from the Earth and no use for it. Velocity to which satellite escapes from Earth's gravity called escape velocity. If kinetic energy of an object launched from the Earth were equal in magnitude to the potential energy, then in the absence of friction resistance, it could escape from the Earth. Escape here, we calculate escape velocity. This one is escape velocity. This one is kinetic energy. This one, and this one is potential energy. Then you make V subject, you can get this value escape velocity from the Earth. The satellite is kept in orbit by its speed. It's continually falling. This is falling. This. But the Earth curves from underneath it. Objects in orbit are said to experience weightlessness. They do have gravitational force acting on them, though. The satellite and all its contents are in free fall, so there is no normal force. No normal force, it means experiencing weightlessness. This is what leads to the experience of weightlessness. This is like a lift in 3 cases. Acceleration here is 0, acceleration is half g, up is going up, the acceleration down, acceleration equal to g. It feels weight. No, this one is not feeling weight. Weight is equal to 0. Weight here mg, weight here half mg. More properly, this effect is called apparent weightlessness because the gravitational force still exists. It can be experienced on Earth as well, but only briefly. All these 3 cases, only briefly. You jump high, or this one, this case, only briefly. In the subsequent, you come down, weight, as previously. This. So only you will feel this one momentarily. Other cases, situations, you will feel this one or this one, you will come down quick. Example, geosynchronous satellite. A geosynchronous satellite is one that stays above the same point on the Earth, which is possible only if it is above the point on the equator. Such satellites are used for TV and radio transmission, for weather forecasting, and the communication relays. Determine A, the height above the Earth's surface such a satellite must orbit, and B, such a satellite's speed. C, compared to the speed of the satellite orbiting 20 km to 100 km above Earth's surface. Period of satellite must be 1 day. Only force on satellite is gravity, so G times mass of satellite, mass of the Earth, radius square. All this we know. And this mass of satellite, and this is centripetal acceleration. This one, this part centripetal force, this centripetal acceleration on the satellite, because it's revolving. Our nouns are V and R. We don't know V and R. But period of satellite is equal to 24 hours. 24 hours times this one. 1 day, this one we have. Speed of satellite, we have, you use the same speed at Earth. This is circumference of the circle over period. Substitute in a formula here, and we can get everything there. So satellite orbits at this distance, that's 8. And also you substitute again, you can get V. The sun's mass determine the mass of the sun given. The Earth's distance from the sun is RAS is equal to 1.5 times 10 rise per 11 meters. Approach equation relates the mass of the sun to the period and the distance of any planet. We use the Earth. Solution: the Earth's period is 1 year. We know period. This one you calculate period, those days. Use like before, previous mass of the sun. You substitute the formula, you get everything. Easy. The Kepler's first and second laws, you have to know how to draw these drawings. Sun, Earth, reference we use Earth or other planets, but you can see. Orbits of planets are ellipses with the sun at one focus. Planets sweep out equal areas in equal times, velocity not constant. Like here, this is laws. Planets sweep out equal areas in equal times, like here, this area. Deriving Kepler's third law, since the centripetal force equals the force of gravity for an orbiting object. This one we saw before. You substitute in these formulas, then you can get what you want. Period you can get there. You can get period divided out. You follow this one. You can get everything here. Kepler's third law, the ratio of the square of a planet's orbit to period is proportional to the cube of its mean distance from the sun. So you have to know how to calculate, how to derive this, and very easy. Yeah, everything is there, so you can understand this one. It's very easy. This table, planetary data applied to Kepler's third law. This is no, it's not needed for your experience and for your experience, interest. You can see this also in your time. Gravitational field exists for every orbit. Gravitational field exists for every orbit that has mass. Field is responsible for gravitational force on objects. Field is force per unit mass. Magnitude of Earth's gravitational field at any point above Earth's surface is that much. At Earth's surface, gravitational field is equal to G. Since gravity is an attractive only force, field lines point toward center of Earth, like this one. Summary: an object moving in a circle at constant speed is in uniform motion. It has a centripetal acceleration. Remember, there is a centripetal force given by this one. The centripetal force may be provided by friction, gravity, tension, the normal force, or others. Normal force, it means there in a banking rod. Normal force there, component of normal force, can get. Or friction, we saw examples. Gravity, we saw. Period, time required for one revolution, frequency revolutions per second. Newton's law of universal gravitation, we saw this one. Remember this mathematical presentation of the law. Satellites are able to stay in Earth orbit because of their large tangential speed. Objects in free fall are said to be weightlessness because there is no normal force, but there is still gravitational force. Like the one there, those three, this one, in this case, no normal force here, only weight force there. No normal force here,
This one is normal force, this one is normal force. Here no normal force, only weight force. Kepler's third law states that the square of the period of revolution is proportional to the cube of the mean distance from the sun. This is the end of our presentation. Thank you. Wishing you all the best in physics and other subjects.